Hi, in this video, we will help to support the activity of conservation of energy springboard. And please feel free to pause the video or rewind if necessary. Conservation of energy is all about the total amount of energy remaining constant. And recall, we're going to be dealing with some individual energies here. So if we have kinetic energy, remember the equation for it is KE equals 1/2 mv squared, and PE equals mgh. So if we have velocity, we have kinetic energy. If we have a height, we have potential energy. Total mechanical energy is the total of your kinetic and your potential energies. So in other words, KE plus PE. This is going to be a common theme we're going to explore with this activity. All right, so let's begin. In this activity, we're going to use a character named Bellyflop Benny to help us not only conceptualize, but quantify these energy transformations. Let's begin. Part 1A. Suppose Bellyflop Benny were to climb a ladder to a diving platform some height above the ground. When he's at rest on the ground, what's his potential energy, his kinetic energy, and label these values appropriately on the diagram. Well, recall, guys, if he's at rest, that means he has no speed. It means he has no kinetic energy. So we can label his kinetic energy as 0. And we also have the fact that he's on the ground, which would be a height of 0, which means he would also have no gravitational potential energy at that point either. Let's go to the picture and label that down at the bottom. PE is 0, kinetic energy is 0, and if we add kinetic energy and potential energy, then 0 plus 0 adds up to a total energy of 0 at the bottom. Notice I'm color coding these energies. Potential energy black, kinetic energy blue, total energy gray. Part B. What kind of energy does he gain by climbing the ladder, and how does he get it? Well, he gains gravitational potential energy and he does this by doing work against gravity. Remember, work is equal to a change in energy. That was work energy theorem we worked on last week. Well, if work is equal to a change in gravitational potential energy, that means his potential energy increased because of the work he did. So every rung he stepped on the ladder, he gained potential energy. But he did that because he did work every rung of the ladder he stepped up. Now, when he dives, so he's diving from all the way up here to down here in the swimming pool. So as he dives, what happens to his potential energy on the way down? Well, his potential energy decreases, and the reason it decreases because it is transforming. Into kinetic energy. We're going to see this play out as we actually do the calculations that are to come. Part 2. Suppose he gains 10,000 joules of potential energy by climbing the diving platform. let's label this at the bottom, or at the top. Potential energy, he gains 10,000 joules of potential energy. I don't yet know the kinetic energy, so I'm going to list it. And I don't yet know the total energy, but I'm still going to list it. How much work was done? Well, again, recall, work was equal to a change in potential energy. So if he gained 10,000 joules of potential energy, he did 10,000 joules of work to actually get up to the top. This is more a conceptual answer rather than a calculation. What is his kinetic energy as he stands? Stands is the key word. If velocity is equal to 0, kinetic energy at the top is equal to 0. Let's label this on the picture. And we have something to go by now. Kinetic energy plus potential energy equals total energy. Therefore, the total energy is 10,000 joules, and it's all potential energy to start with. Suppose he dives into the pool of water at the base of the ladder. What's his potential energy right before he dives, labeled on the diagram? What's his kinetic energy right before he hits the water, labeled in the diagram? Let's take a look at the bottom. Well, his height right before he hits is exactly the same as the height before he climbs the ladder. Therefore, his potential energy will be back down to 0. However, because total energy remains constant, and the total energy must remain at 10,000 joules, remember it was 10,000 joules to begin with, right? That must mean that the kinetic energy started from rest and increased to 10,000 joules. In other words, let's look at the scenario of what happened here. We started with 10,000 joules of potential energy, and we can see that it has converted into 10,000 joules of kinetic energy. The total energy, as you can see, has remained the same. Okay, part C. Determine label the values of Benny's potential and kinetic energy halfway down. Okay, so let's go to the halfway point. The halfway point would be here. Okay, and at that point, we have half potential energy and we have half kinetic energy. That makes for a pretty easy calculation. The potential energy would therefore be half of what it was at the top. In other words, it decreases from 10,000 to 5,000. The kinetic energy should also be half. Well, it should be half the kinetic energy you had down here when it converted to. So it should also be 5,000. So much so that we understand that the sum of these two should be the total energy, which should again add up to 10,000 joules. What's the common theme here? Total energy remains constant. Determine and label the value of Benny's potential and kinetic energy when he's a quarter of the way down. Let's go up to the top. Quarter of the way down would be right here at this spot. Well, quarter of the way down, guys, you have a quarter loss of potential energy. That means you've decreased your potential energy by a quarter and you've increased your kinetic energy by a quarter. So that means your potential energy is down to 7,500 joules. That's a quarter less than 10,000. And your kinetic energy is up by the exact same amount the potential energy you lost. So we lost 2,500 joules of potential energy. Coincidentally enough, we gained 2,500 joules of kinetic energy to keep the same total energy of 10,000 joules. When Benny reaches the level shown at the star, his kinetic energy is 8,200 joules. What's the potential energy at this level? Well, here's the star. We don't know his potential energy, but we do know his kinetic energy is 8,200 joules. And we also know that the sum total of the energy, the total energy, has to remain at 10,000 joules. So to figure out the potential energy, we need to subtract 8,200 from 10,000. And in doing so, we get a potential energy of 1,800 joules. When Benny reaches the level shown with the circle, his potential energy is 6,400 joules. Determine the kinetic energy at this point. Well, you'll find the circle up here. The potential energy was reported at 6,400 joules. The kinetic energy is what we're trying to find. And we can see that the total energy, again, needs to remain constant, 10,000 joules, yeah? So, if that's true, then the 6,400 joules taken away from 10,000 joules results in a complement of 3,600 joules. So that, again, potential plus kinetic has to add up to the total energy. Now let's take a look at the second side of the page, and let's look at solving for very specific variables. Benny has a mass of 100 kilograms, and we're going to use G as 10. So the value of mg, which is Benny's weight, would be 100 kilograms times 10 meters per second squared, which is actually 1,000 newtons. We're going to need this when we do our calculations, okay? So just hold on to that little calculation there. Now, something to think about when we are doing a potential energy calculation. mgh. And you are asked to solve for h. You have to divide the mg both sides. So h is going to be the potential energy divided by mg. Right? We have to divide mg both sides. Similarly, if we have to solve for kinetic energy, and it's 1/2 mv squared, and let's say I want you to solve for speed, then I need to multiply by 2 to get rid of the 1/2, divide by mass, and then square root. And just as we were shown last week, we could rewrite this equation for velocity as v equals the square root of 2 times the kinetic energy over the mass. Okay? So we're going to be using these equations to do the specific analysis below. Part 4a. What is the height of the diving platform? Well, again, if I'm looking for, that's going to be height is equal to potential energy divided by mg. Recall, guys, the diving platform, you had a potential energy of 10,000 joules all the way up here at the top. So if I take the 10,000 joules divided by mg is 1,000 newtons, we can see we end up with a 10-meter high diving board. Okay, what's the height of the circle? Same equation. The circle, if you recall, had a potential energy of 6,400 joules. Again, over 1,000 newtons, about 6.4 meters off the ground. And then it says, when Benny has a kinetic energy of 7,700 joules, what's the height above the ground? So it's the same calculation, but here's the catch. You got to figure out potential energy from the kinetic energy given. Now remember, total energy is equal to kinetic energy plus potential energy. So I can find this missing potential energy by taking the total energy of 10,000 and subtracting the kinetic energy of 7,700. So the potential energy I'm going to use in this problem is 2,300 joules. Again, over 1,000 newtons. It's about 2.3 meters above the ground. Part 5 deals with a speed calculation from kinetic energy. So what is the impact speed before hitting the water? So we're using the equation for kinetic energy and solve it for speed. We have speed is equal to 2 times the kinetic energy over the mass, and then take the square root. So 2 times 10,000 is the kinetic energy right before hitting the water, over the 100 kilograms of mass. This is important to note the difference. mg is mass times g, or 1,000. Benny's mass itself is 100 kilograms. Remember, kilograms is the unit of mass. Well, if we take 20,000 divided by 100, we get 200. Upon taking the square root of 200, you get about 14.1 meters per second is the speed of impact. Going that fast, that's about 20-something miles per hour, almost 30 miles per hour with a belly flop. Oh, that's going to hurt. That's going to hurt a lot. Now, when we're halfway down, that means the kinetic energy is half. Remember, the kinetic energy was 5,000 joules halfway down. So velocity is equal to 2 times 5,000 joules over the 100 kilograms of mass. Well, 2 times 5,000 is 10,000. Divided by 100 is 100. Square root of 100 is 10 meters per second. And then it goes on to say, if Benny has a potential energy of 8,100 joules, what's the speed? Well, we got to find the kinetic energy first. So again, use the total energy, 10,000 joules minus the 8,100 joules of potential energy gives you the remaining 1,900 joules of kinetic energy. Remember, the two of these must add up to the total energy as we modeled on the front side. Velocity is equal to 2 times 1,900 over the mass. And 2 times 1,900 is 3,800. Divided by that is 38. Square root of 38 is a little bit more than 6, about 6.2 meters per second. Now in part 6, well, we're starting with a speed and we're trying to figure out height. So to do this, what we're going to do is we're going to use the kinetic energy from the speed, then find the potential energy, then do the height. So ultimately, the equation for height is the potential energy over mg. Let's find the kinetic energy first, though. 1/2 times 100 times the speed, 5 squared. Well, 5 squared is 25, times 100 is 2,500. Take half, we have 1,250 joules of kinetic energy. The potential energy is the total energy of 10,000 minus 1,250, which is about 8,750 joules. That is our potential energy for the height calculation, or about 8.75 meters high. Again, if you feel like I'm going a little too fast, rewind the video or pause as needed. Lastly, if we have to find the speed, we need the kinetic energy, 2 times the kinetic energy specifically, divided by the mass. So let's use the height to find the potential energy. So it's Benny's mass times 10 times height. Well, 2 times 10 times 2.4 is 2,400 joules. And we know that kinetic energy would be the total energy of 10,000 joules minus 2,400 joules, or about 7,600 joules. Completing the calculation, we have 2 times 7,600 joules over 100 kilograms. 7,600 times 2 is 15,200. Divide that by 100 is 152, square root of which is about 12.3 meters per second. So to follow up on this activity here, one thing I'd like you to notice, the potential energy decreases all the way down. We lose potential energy all the way down. At the same time we're losing potential energy, we're gaining kinetic energy all the way down because we're accelerating, we're gaining speed. And lastly, the main idea is that the total mechanical energy remain constant the whole way.